Till now, in fundamental interaction, we have discussed in detail two fundamental interactions. First one was gravitational interaction, and secondly, we have seen the electromagnetic interaction. Now, in this lecture, we will see the important characteristics of the remaining two interactions, and those two interactions are weak interaction and a strong interaction. In fact, you have studied the process of beta decay in earlier lecture in very detail. And while discussing the process of beta decay, you have seen that actually a weak force acts inside the nucleus between the nucleons, and that weak force is responsible for beta decay. In fact, the weak force which is operating between the nucleons and that due to that interaction beta decay is resulted, that is called actually weak interaction. But that was only an example. In broad sense, you can say that this weak interaction, due to this weak interaction, we can see that the leptonic decay of strange and non-strange particles, and at the same time non-leptonic decay of the strange particles. These decay are actually due to weak interaction. It means when you talk about the decay of leptons of strange particles and at the same time of non-strange particles, and the decay of non-leptonic particles, or you can say the decay of non-leptons into strange particles, these type of decays are due to weak interaction. In fact, beta decay is in fact one of the important examples of this weak interaction. Okay. We can see that this leptonic decay of strange and non-strange particles and non-leptonic decay of strange particles, actually both of these decay modes are 4 fermion process. You can see, for example, in beta decay, you know, a neutron is converted into a proton, and at the same time electron and anti-neutrino are produced, are created and emitted. And you can see in this reaction all the 4 particles, that is neutron, proton, electron and anti-neutrino, all these are fermions. So we simply say that in this type of decay process 4 fermions are produced. So this is actually called the 4 fermion process. Okay. Now you know that for every interaction we define a coupling constant, and that coupling constant actually determines the strength of that interaction. So in the case of weak interaction, we again define a dimensionless coupling constant, and that dimensionless coupling constant is defined by this equation. You can see this is actually equal to Gf square over h bar c whole square times m pi c over h whole to the power 4. In fact, here this Gf is what? You have studied this Gf while the study of beta decay. When we have studied actually the Fermi theory of beta decay, then we have calculated the value of this quantity Gf, and you have seen that the value of Gf on the basis of Fermi theory of beta decay, it is found to be 1.435 into 10 to the power minus 62 joule meter. Okay. Actually, this is a numerical constant for weak interaction. Now, when you will substitute the values of all quantities appearing in this expression, where m pi is actually mass of a pion, then the after simplification we get the value of this coupling constant, which is equal to 5 into 10 to the power minus 14. As you can see, this coupling constant is very small. This is very small, negligibly small, and that's why this weak interaction is actually weak in real sense. It is not as strong as electromagnetic interaction or a strong interaction, but in comparison to those two interactions, it is weaker. Okay. Now, you have to remember some of the important constants for this weak interaction. You should remember that the characteristic lifetime of this weak interaction is 10 to the power minus 8 seconds. These are some informations which you have to remember. And the characteristic cross section for this interaction is 10 to the power minus 12 millibar. Okay, and its range is less than 10 to the power minus 17 meter. Okay, it is almost of the order of 10 to the power minus 18 meter. So you can say that it is a very short range force. This force will exist only when we are talking about the particles inside the nucleus, and even inside the nucleus their separation is even less than the nuclear diameter. Okay, so this is a very short range force. Okay. Now, one of the important characteristic of this weak interaction is that this force is never attractive. This weak interaction is never attractive. It means this force will be always repulsive. Okay. Now, you know that every interaction is mediated by some particle, which is called actually the field particle for that interaction. And for any interaction, the field particle is definitely boson. As you have studied earlier, that the gravitational interaction is due to graviton, the electromagnetic interaction is due to photon, and the strong nuclear force acts due to the mesons. These are actually the agents or the mediating particles which actually mediates the particular interaction. Like that, this weak interaction is also mediated by a boson, and that boson is called actually the vector boson, having a mass of the order of 80 to 90 giga electron volt per c square. Okay, and this boson is known as intermediate vector boson. Okay, and these are what? These are W plus, W minus, and Z0. Okay, all these three intermediate vector bosons have the same spin, and its spin is equal to 1 or h bar. Okay, so you can say that the particle or the mediator or the mediating particle responsible for this weak interaction is what? That is actually the intermediate vector bosons W plus, W minus, and Z0. Actually, in the laboratory of CERN, first of all, these intermediate vector bosons were detected in 1983. So after 1983, when the existence of these vector bosons were confirmed, then the idea that these vector bosons are the mediating particles for weak interaction was confirmed. Okay. Now, I have shown here by this diagram the decay process of the neutron into proton by taking the mediating particle W minus. You can see this is your neutron, and this neutron actually shoots out two particles. One is this proton and another is the filled particle W minus, and this W minus then actually decayed into E minus, that is electron or negative beta particle, and the neutrino, or you can say the anti-neutrino. Okay. Now, this weak interaction is broadly classified into two classes. First one is called charged weak interaction, and the second is known as neutral weak interaction. Charged weak interaction and neutral weak interaction, these are basically the two broad classes of this weak interaction. When you say charged weak interaction, in fact in such type of weak interaction there is a change of electric charge. Okay. But when you say neutral weak interaction, it means there will be no change in unit electric charge by a particle involved in this process. Now we will actually see some of the important examples for this charged weak interaction and the neutral weak interaction. You can see actually these examples are very important for your examination purpose when the question is asked by citing some of the nuclear reactions, and you have to say that what type of interaction is playing a role for that decay process. Then you should use this idea to solve such a problem. So let us see some of the important examples of charged weak interaction. First of all, we are observing here the purely leptonic charged weak interaction. In fact, when you say that the charged weak interaction is purely leptonic, it means here only leptons are involved in the decay process. So you can see some of the important examples here. Mu minus is decayed into electron, anti-electron neutrino, and the mu neutrino. Okay, and all these are actually leptons, and so this is just an example of a purely leptonic charged weak interaction. Okay, and the another example is mu plus is decayed into E plus plus nu E bar. Okay, and the third one is nu mu plus electron equal to mu minus plus nu E. Similarly, nu E plus electron, that is equal to nu E plus electron. Okay. Now we will see some of the important examples for charged weak interaction which is semi-leptonic. When you say that the process is semi-leptonic, it means in fact in this processes you will see that there will be actually hadrons and lepton pair involved in such reactions. So you can see the nuclear beta decay. Here neutron is transformed into a proton, and at the same time electron and anti-neutrino are produced and emitted, and you know that this neutron and proton are hadrons, and on the other hand this electron and anti-neutrino are leptons. So you can see that a pair of hadron, neutron and proton are involved in this reaction, and at the same time the another pair is of leptons, E minus and nu E bar. Okay. Now the another example of this semi-leptonic weak interaction is electron plus proton equal to neutron plus neutrino. Here again you can see neutron and proton, this is just a pair of hadron, and electron and neutrino, this is a pair of lepton. Again we will you can see this mu capture, mu minus plus p equal to n plus mu nu. Again this p and n is a pair of hadron, and mu minus and nu e, nu mu, this is a pair of lepton. Okay, so these are the important examples of the weak interaction. Now, the second class of this weak interaction you have seen is neutral weak interactions, and I have mentioned here again some of the important examples of this neutral weak interaction. You can see the first one is neutrino-lepton scattering. Neutrino-lepton scattering. You can see when actually the neutrino nu mu is scattered by this electron, then the identity of the particle does not change. This is nu mu plus electron. Similarly, you can see the another example, which is neutrino nucleon scattering. Here actually this neutrino is scattered by this neutron, and this is also an example of a weak interaction. Actually, when we see these two examples, actually only weak interaction takes place here. But now we will see the another example, which is lepton-lepton scattering. You can see E plus plus E minus, that is mu plus equal to mu minus. And electron-nucleon scattering, you can see E plus N equal to E plus N. Actually, when these two processes takes place, the interaction is not purely a weak interaction, but it is accompanied by the electromagnetic interaction too. So these two examples, in these two examples, we simply say that these processes will complete with the electromagnetic interaction, not only by the weak interaction. Now, a most important example of this weak interaction you can take hadron-hadron interaction. Here neutron and neutron, or you can say that nucleon is transformed into the same particle, and this interaction actually is completed not only by the weak interaction, but it is completed with electromagnetic interaction and a strong interaction too. Okay, a strong interaction. So in brief, I have mentioned here the important characteristics and important examples of the weak interaction. You should watch the video seriously and note down these things and remember, because in this video you will get some information which you have to remember. Okay, now we will see the concept of another and important interaction, which is called a strong interaction. Okay, when you say a strong interaction, that means simply the strong nuclear interaction. Okay, you know that actually the nucleons inside the nucleus is due to an interaction which is called actually the strong nuclear interaction. In fact, a strong interaction acts between a pair of hadrons. When you say that inside the nucleus there are nucleons, and those nucleons you know are hadrons, so interaction between neutron and neutron, interaction between proton and proton, interaction between neutron and proton inside the nucleus, that is actually a strong interaction. But neutron and proton are just a hadron, so you can say that this strong interaction actually acts between a pair of hadrons. For example, inside the nucleus, as I have told you, the pair of hadron will include neutron and proton. Similarly, the strange baryons, that is lambda and sigma particles, are another pair of hadrons between which the strong interaction will take place. Similarly, the pair of mesons, that is pi meson and rho meson, this is another pair between which a strong interaction takes place. Okay. And similarly, the strange mesons, these strange mesons are K, and between two kaons, this interaction also takes place. Okay. One of the important characteristic of this strong interaction is that this interaction is always attractive. Okay, you have seen that the weak interaction is never attractive, but this strong interaction is always attractive, and at the same time it is independent of charge. But when you say that this is independent of charge, then you will see later on the basis of quark model, we will see that this statement that a strong a strong interaction is independent of charge, this statement is apparently correct. It is not, in fact, correct 100%, because we will see that the charge symmetry, or you can say that the charge independence of this strong interaction is apparently violated, particularly in case of the hypernuclei. But we will see that fact later on. But when you talk about the nuclear force inside a nucleus, then we simply see that the force between two protons, this is a proton, this is a proton, and force between these two protons, and similarly the force between two neutrons are same. Okay, and force between a neutron and a proton is also same. Here protons are actually charged particles and neutrons are neutral particle, chargeless particle. But as the force between two protons and two neutrons, or a neutron and a proton inside the nucleus is same, so on this basis we simply say that this strong nuclear interaction is charge independent. But as I have told you, we will see later on, just at the end of this lecture, that this strong interaction depends to some extent on charge. So it is, in a strict sense, we cannot say that this strong interaction is charge independent. Okay. Now, this is also a short range force. It is operative, it is effective only in the dimension of nucleus. So inside a nucleus, this force is effective, but if the nucleons are outside of the nucleus, then this force is much weaker in comparison to the electromagnetic force. So we simply say that this is a short range force, and as a particular value you can say that its range is of the order of 10 to the power minus 15 meter. It means this force will be appreciable, effective, when the separation between the two particles between which a strong interaction takes place is of the order of 10 to the power minus 15 meter. Okay. Now you have studied till now three interactions. You have seen in all three interactions, on the basis of field concept, that any interaction is mediated by an agent or by a particle, which is actually called the mediator of that interaction. And all those mediating particles are actually bosons. So this strong interaction is also mediated by a boson, and that boson is actually called pion, and its spin is 0. Okay, so you can say that the field quanta for a strong interaction is pion, and it is its spin is 0. In fact, this theory, in fact, the concept of pion was introduced by Yukawa, a Japanese scientist. Yukawa's meson field theory you have studied. So this pion is the mediating particle, or the particle responsible for this strong interaction. In fact, when two nucleons interact one another, a pion is shoot out, and the exchange of pion is responsible for this interaction. Okay. Again, you know that strength of any interaction depends on the value of a dimensionless coupling constant, and for this interaction, the coupling constant, which is actually a dimensionless number, is equal to g square over 4 pi h bar c. Actually here g in case of a strong interaction is just equivalent to charge in case of the electromagnetic interaction. So you can say this g plays the same role in case of a strong interaction as the charge plays in case of electromagnetic interaction. Okay. So the value of this coupling constant is almost 14. So you can see that the value of this coupling constant is very large in comparison to the value of coupling constant for electromagnetic interaction, for weak interaction, and for gravitational interaction. In all those interactions, this coupling constant was smaller, and in this case you can see that its value is much greater than the coupling constant of the remaining three interactions. And that's why we say that this force is very strong, because the strength of interaction depends on the value of this coupling constant. Okay. Now this strong interaction is also explained on the basis of quark model. We will study in the forthcoming lecture the quark model in the chapter elementary particle, and you will see that when we study the elementary particle on the basis of quark model, then it is seen that this strong interaction is just due to the exchange of color quanta, which is called gluon. On the Yukawa's meson field theory, you have just seen that this force is due to the exchange of pion, but according to quark model, a strong interaction is mediated by gluon. So you can say on the basis of quark model, gluon is the particle or the field quanta responsible for the strong interaction. So this strong interaction is actually due to the exchange of gluon, okay, on the basis of quark theory. Okay. And this gluon is actually again a boson, and its rest mass is 0, just like photon, and spin is equal to 1. Okay. Now, when a strong interaction takes place, there are so many quantum numbers which remain conserved, and in the forthcoming lecture we will actually discuss in very detail the different conservation principles. But here, just as an information, I have mentioned that what are the quantum numbers which remain conserved during the strong interaction. You will see later on that the baryon number B, the charge Q, hypercharge Y, parity pi, isospin T, and the third component or Z component of this isospin, that is Tz or T3, remain conserved during this strong interaction. Okay. So these are the quantum numbers which do not change during a strong interaction. Okay. Now remember these informations. The characteristic lifetime of this interaction is 10 to the power minus 24 seconds. This is very short, and its cross section is almost equal to 10 millibar. Okay. Now, as I have told you earlier that this strong interaction is charge independent, because we see that the interaction between neutron and neutron, proton and proton, and a neutron and a proton inside the nucleus is same. And that's why we simply say that a strong interaction does not depend on charge. But you know, if a nucleus contains nucleons and along with these nucleons, if one or more strange particles like lambda particles are also present in a nucleus, then such a nucleus is called hypernucleus. You can see that normally the people say that inside a nucleus there are nucleons, that is neutron and protons, but it is possible that inside a nucleus, apart from these nucleons, one or more strange particles like lambda particles are also present. So all those nuclei in which along with the nucleons, strange particles like lambda particles are also present, then such nuclei are called hypernuclei. Okay, such nuclei are called hypernuclei. Now, let us consider that there is a hypernuclei. So in that nucleus, there will be proton, there will be also neutron, and there will be also lambda particles. So there will be interaction between this lambda and neutron and lambda and proton. Okay, and it is seen that the strength of the force, strength of the interaction between lambda and neutron and lambda and proton are not same. It means this interaction, lambda and n interaction and lambda and p interaction, these two interactions are not of equal strength. Those are different. So here you can say that actually the neutron and proton has different charge states, and that's why the strength of the interaction between strange particle lambda and neutron and lambda and proton are different. So in this way we see that this strong interaction depends on charge to some extent, and that's why we simply say that this difference in the interaction, strength of interaction between lambda and n and lambda and p actually implies that this is against the charge symmetry. And so when you say that nuclear force or the strong force is independent of charge, such a statement is apparently true. It is not 100% true, or you can say that this statement is not absolute. Okay, so I have mentioned it here. You can see it is observed that the strength of the interaction lambda n and lambda p are unequal, not same, which is against the charge symmetry. And thus the concept that the strong interactions are purely charge independent is not absolute. It is not absolutely correct, you can see. So after this lecture we have completed the discussion on the fundamental interactions. You have discussed in these lectures the four type of fundamental interactions. Now in the forthcoming lecture we will see a very important concept, and that will be actually the concept of symmetry and conservation principles. Actually you will see that any conservation principle is due to some type of symmetry. Symmetry of something is responsible for a conservation principle. So how symmetry leads a conservation principle, in first lecture we will see that, and after that we will see the discussion on different conservation principles in particle physics. Okay.